I'm either getting old or I'm tired because I need to get my glasses here. I don't know which one it is. I'll pretend like I'm tired. So last time we kind of started at the beginning, right? Strong form, weak form. Talked about this element deal a little bit. And mentioned this topic of isoparametric mapping. It's kind of where we left off. So now I'm going to add in another little piece where we kind of left off, but I'll start at the beginning again so we can see the whole problem every time for your notes. Or we go going through the process, and we'll go a little bit farther than we did last time. Okay, yeah, that's how far it goes. So let me get our board up and go. Okay. Nada. Again. Uh-oh. Okay. Or sorry, I didn't ask. Are you guys able to see the board?
Yep.
Okay. So we'll start off at the beginning again, strong form. For one-dimensional elasticity. And once again, it's just a simple beam. With some stress. And this is a body V of X, so body force on it. And the constraints of our problem are, again, elastic modulus times the area times strain. And we're going to take the derivative of that plus our body force is equal to 0 from 0 to L. This is our domain. And we're going to have a boundary condition that the displacement at 0 is equal to 0. And we're going to state that elastic modulus at the end of the beam times our strain at the end of the beam is equal to our stress. So nothing new. And our weak form, which we've previously shown is equivalent, that'll recover the exact solution, is find delta such that all of this stuff are bilinear functional For all W contained in this funny V space, and our bilinear functional is equal to the integral from 0 to L, elastic modulus times our area times strain, the derivative of our weight function, dx, and our linear functional is equal to the integral from 0 to L, body force weight function dx, plus stress area at the end of the beam, weighting function at the end of the beam. And in delta, we have these, for displacement, we have to create some kind of boundaries, right? Displacement field has to be H1 continuous from 0 to L, where displacement at 0 is equal to 0. And in this funny V space, our weighted space, W, our weighting function, is also H1 continuous from 0 to L, where we're saying that the weighting function at 0 is equal to 0. That's our weak form. And the finite element method in 1D, we have elements and we have nodes. And I'm going to say that we have 4 elements. And element 1 is associated with nodes 1 and 2. Element 2 is associated with nodes 2 and 3, 3 and 4, 4 and 5. And obviously this is in a, this numbering scheme is in a global, this is global nodal numbers. And remember, we just have this so we have 1, 2, 3, 4 are elements, and 1, 2, 3, 4, 5. And this represents a nil equals to 2, right? And this is a considered a linear element. And what did nil equal to 3 look like? There's probably a better way of doing it. Element is the same size as 3 nodes. So this would be considered a nonlinear element. And for our linear element, x1e, e, x2, e, and x. This is LE, it's the length of the element. E around the circle, that's our element. And we're going to map to this C space. So remember the element maps and the nodes map. Something like that. And then we apply the Rayleigh-Ritz method. And we get this U, our displacement of the element, to the 8th in C space is equal to the sum of I is equal to 1 to N. NI C UI to the E, which breaks down to N1 C, N2 C, and this is a U1E, U2E. So I'm writing this a little bit different than what we did last time. For Nel equals to 2. So the way I've written this here, this is a matrix. And this is equal to NE DE, where our shape functions are our NE. Remember, these are Lagrangian shape functions. That guy and that guy. Our displacement fields at node 1 and node 2. It's not a 2 here, that's supposed to be an E, U2 to the E. So this is just displacement, displacement field for node 1 of our element, and displacement field for node 2 for our element. This is DE. So
the E superscript just means element?
Yeah. So we can write this as U E to the H C is equal to this NE DE. Let me clean this up. So what we're doing is we're kind of building things together and creating these relationships, or putting them into matrices and stuff, kind of getting it ready for this thing that we're going to call on Monday an assembly method. And it's basically, how do you take the solutions for each one of these points and assemble them in together to make sense of it. So from here, we do isoparametric mapping. And that is for x, x to psi is equal to the sum of I equals to 1. Now, ni psi xi e is equal to n1 psi x1 e plus n2 psi x2 e. And this will give you n1 psi n2 psi and x1 e x2 e. This is 4 now equals to 2. So this leads to x psi is equal to n e x e. And x is equal to 1 minus psi over 2 x1 e plus 1 plus psi over 2 x2 e. Because n1 psi is equal to our shape function, if you remember, and n2 psi is equal to our other shape function. And now, if we say we're looking for dx dc, so we're looking at the derivative of this, that's going to equal minus x1 e over 2 plus x2e over 2, which is equal to x2e minus x1e over 2, which is equal to LE over 2. Let's see if that's true. So x2e minus x1e over 2 is LE. Remember we said LE was right here is our element. So we're saying x2 minus x1 over 2 is that. And this is actually equal. This is called something. This is the Jacobian matrix. This is a Jacobian matrix. And we'll see that a little bit. We'll see that on Monday. Actually in matrix form. I'm sorry, Tuesday. Either Tuesday. Yeah, depends on how far we get on Tuesday. Either Tuesday or next Thursday, we'll see it, and actually we'll see this Jacobian pop up in the full matrix form. But we need the derivative of our Rayleigh-Ritz method, partial over Rayleigh-Ritz, C of x we're going to say that's equal to D UEH DC times DC DX. Therefore, UEH prime is equal to D UEH over DC times 1 over the Jacobian. And the Jacobian is LE over 2 for this one, which is equal to D DC NE DE times 2 over LE is equal to D NE DC 2 LE times DE. Excuse me. And this narrows down to another matrix, DNI DC. So remember our shape function, DN2 DC 2 LE DE. And for our problem, this is equal to minus 1/2 plus 1/2 2 over LE dotted with DE, which is equal to 1 over LE minus 1 DE. And this this whole term right here, we're now going to call BE. So UEH prime is equal to BE DE. So for this particular case, we have the derivative of our shape function with respect to psi for the first node, or shape function number 1. And then the second term, we have the derivative of our shape function, our second shape function with regards to psi. And that's times 1 over the Jacobian. And our Jacobian is this isoparametric mapping formula right here, where we're taking the derivative of that with respect to psi. And that whole thing times DE, and DE was our displacement at node 1 and our displacement at node 2. So you guys see that these are building up to be some pretty horrible matrices with a lot of things behind the scenes. And this BE is called the strain displacement matrix in 2D and 3D. So the same thing can be applied in 3 dimensions. Excuse me. It's just this matrix gets bigger. Actually, yeah, we are going to see the assembly method kind of grow out of this today. Okay. So now, now what we have is we have this, or we're setting up is we have this discrete weak form. And when I say discrete weak form, if we go up here to the top where we started tonight, we have the strong form, which is just this general equation relating a one-dimensional beam that we're putting in tension, right? It's just the elastic modulus times the area times our strain. So the derivative of that plus our body force has to equal 0. And then we created this weak form. So this is valid from 0 to L, right? It's the entire domain. Omega is from I guess I should have wrote that L. So 0 to L. And then we have this weak form, which we're saying is made up of this bilinear functional and a linear functional that uses this W, which is a weighting function. That's going to help us solve this. So now we're talking about this different form of the same equation that has this weight function W in it. And, you know, we kind of arbitrarily set some things saying this weight function 0 at 0. And some of the other problems I think that we showed you is we said that the, did we say that W at 1 or W at L was also equal to 0, depending on, I think, on the other solution, or it was equal to 1 or something like that. It depends on the problem, but so then we said, okay, we have this, you know, part here, and we said that we're going to break it up into 4 elements and 5 nodes. Well, there's node 1, node 2, 3, 4, 5. So we get 1, 2, 3, 4 elements. So this is all we're doing. I mean, I drew this beam as two-dimensional, but it's we're solving a problem like it's one-dimensional, right? And then this was element 1, 2, 3, 4, and nodes 1, 2, 3, 4, 5. So strong form applies to everything. Weak form applies to everything. And then we say, oh, by the way, we're going to break this up. The finite element method, we're going to say, okay, we're going to break this up. We're assuming it's one-dimensional, and we're going to break it up or slice it. And where we cut it, we're basically going to have nodes, these things we call nodes. And then in between those, we have elements. And oh, by the way, I have to do this mapping to go from a global coordinate system for our part to a local coordinate system in this C space. So we're doing that. And then it's like, okay, now we're gonna, there's this other method called the Rayleigh-Ritz method where we're gonna introduce these shape functions. And the shape functions, remember, you know, at the node, the shape function is 1, and at the neighboring node, it has to be 0. So it goes from 1 to 0. And then we have some new definitions of how this what this shape function matrix looks like. So we're calling it NE. We have some isoparametric mapping that maps that puts together our X XC mapping. So we know what that looks like. And when we take the derivative of that, we get this thing called a Jacobian that we're then going to plug back into our Rayleigh-Ritz method. Now, when we're down here and we're looking at this UEH prime BEDE, we are no longer in a global sense, right? We are down at an element level. Anything that we're talking about right now, we're at the element and we're trying to understand what's going on at that elemental level. We're no longer talking about that whole beam. We're talking about a very specific element within the beam. Is everybody there? We're zoomed in, we're into the mesh, and we're looking at a single element. So because of that, we now have a different form of our weak form, and it's a discrete weak form. You could almost call this, we're more at the elemental form, but it's called discrete because we're getting ready to solve it numerically. So this discrete form, we have a bilinear functional, and it's U of H, W of H is equal to L, W of H. And U of H is equal to a trial solution. And W of H is equal to a test function. And now we're going to introduce something new again. And I'm going to say that the sum from E equals 1 to num L is the integral of our domain of our element, elastic modulus, area, the Rayleigh-Ritz displacement, element, prime, our weight function, or our weight test function of the element, prime, dx is equal to the sum E equals 1 to num L the integral over our domain of our element B WE of H dx plus we'll bring our stress in, area, test function at L. This summing is called assembly operation. And we refer to it as this capital kind of A with 2 slashes through it. E equals 1 to num L. So this is just kind of a way that you can see this written that is this whole thing. This is the assembly process for going through and doing our calculations at every nodal value for every element. And we're going to say that our discrete weak form for element E is the integral over a domain of our element E A UEH prime WEH prime dx is equal to our linear functional B WEH dx plus sigma 0 A L WEH L. And this guy here is non-zero only for E equals num L. And let's remind ourselves of what we have. Element 1, 2, 3, 4. So 1, 2, 3, 4. Nodes 1, 2, 3, 4, 5. And let our Rayleigh-Ritz method C equal to NE C DE. And this is our trial function in element E. And then we have WEH C, so this was our weight function, is equal to NE C WE. And this is our test function in element E. And this guy is arbitrary. It's a test function. We set it to be whatever we want to get the solution. Therefore, the integral over domain of our element EA WH prime UEH prime dx is equal to the integral of our domain of our element BWEH dx plus sigma 0 A AL WEH L. And once again, non-zero for E equals num L. Where our trial function, the derivative of our trial function was equal to B E D E, and the derivative of our test functions was equal to B E W E. So we get the integral of over our element EA BE WE transpose BE DE dx integral of omega EA WE transpose BE transpose BE transpose DE dx. This is a 1/2 matrix. This is a 2/2, 2/2, 2/1 is equal to the integral over our element of B WET or transpose NE transpose dx plus our stress at the end WE transpose NE transpose at x equals to L. And this is equal to sigma AL for the last element. So we get WE transpose is the integral of our element BE transpose BE DE dx minus the integral over our element B NE transpose dx minus sigma naught AL NE transpose equals L is enforced to be the 0 vector. Therefore, everything inside here, those parentheses, we're enforcing to be 0. Or the integral over our element EA BE transpose BE dx yeah, I'm gonna write it that way. I'm gonna write this out a little bit. DE is equal to the integral over our element B NE transpose dx plus sigma naught A L NE transpose L. Therefore, KE DE is equal to FE. And you remember that term right there is KE. Well, it's in the form. We didn't have this BE transpose BE in there. This DE right here is still the same. And this guy here is our elemental or our element force vector. So it's not the force applied to the body, it's the force at the element. So depending on how things are redistributed. This KE is called our element stiffness matrix. And for L equals to 2, which is what our problem was, we have KE is equal to EA, the integral from -1 to 1, BE transpose, BE JDC, so Jacobian, and then pulling in our our derivative of our C space, where dx, so see I replace this dx right here? I don't want to jump too far here. This dx right here, what I'm kind of showing you right here, dx is equal to derivative x with respect to z dz, which is equal to the Jacobian times our dc. So that's where that term comes in, Jacobian dc. And this is equal to EA, the integral of -1 to 1 over LE, 1 minus 1 over LE, minus 1, 1, LE over 2, DC is equal to EA, 1 over LE squared. And we get a 1 minus 1 minus 1, 1 LE over 2 times 2. So this 2 and that 2 cancels. That LE cancels that square. Where's my mouse? There's my mouse. So KE is equal to EA over LE, 1 minus 1 minus 1, 1. So this is at the elemental level. So this is for a single element. And so remember, because we have an E here, this is KE. At some point, at some point on Tuesday, we need to assemble KEs into K. So remember, we talked about this K before. And so it's K is equal to this assembly process from E equals to 1 to num L Ke. And is equal to A E equals to 1 some num L Fe. So we have to assemble this K matrix and this F matrix at the global level for all of these elemental levels. And, an example would be, you would have this K matrix is equal to, like a K1. Well, it could be like a K, like it was multidimensional. This could be a K11, K12, K13, K14, and this would be like a K21, K22, K23, K24. You guys kind of get the gist of that. So you have to assemble these elemental stiffness matrices back into the global stiffness matrix in order to show results. And we have to do the same thing for the force function.
Professor, on the 2 by 1, that 1 over -1, and then you multiplied it by the -1, 1. Are you just multiplying those two matrices to get those two matrices to get the
Yeah.
Would your signs
you're integrating it.
after
You have to integrate it, and this is what you get
okay.
after integration. Yeah.
Thanks.
Yeah, but remember this matrix, these are basically the values of your shape functions that are embedded in here. Remember, they have to be 1 and -1. Remember, if you go all the way back to, we didn't write it out today. We had in our isometric isoparameter, so in our X space, and then we have our C space. Remember, this was like I don't know, whatever we want to call this. We can call this 1 and 2. This happens to map to -1 and 1. This mapping in C space, that's what this matrix is. It's just that mapping.
That's interesting. It's just like the axial stiffness from mechanics of materials, but in a matrix for each element.
Yeah. And this Jacobian thing is interesting because it's just the partial derivative of that basically change of that mapping, right, of each one of the components. So when you're doing ANSYS or Abacus or whatever, and you have a problem with your Jacobian matrix, it's specific to this isoparametric mapping. There's an issue with that mapping, and it's looking at the derivatives to do that because it's, because the Jacobian actually expands to this matrix, and it's a partial derivative. So you would have, like a D. I'm just making something up. This could be like a D X11, D Z1 or something, and then D X12, D C2 or something. It's these partials that fill in this matrix, but it has to do with this mapping from an X coordinate system to this C space at the elemental level. But it's taking the partial derivative of it, which is, if we remember, what is the partial derivative? It's looking for continuity in that mapping at a very, very high level. This is, what it's making sure of is that we can go from 0.1 to 0.2, and we don't care about the path. how we get from one to the other. We're just making sure that we get from here to here without a discontinuity. That's a continuous path. That's really what we're doing. So when you're doing a finite element solution and they say there's something going on with your Jacobian, they're just checks and balances that they found that, you know, if that Jacobian doesn't look a certain way, that you'll get an error flag and that you have to check your solution. So something's not right. Maybe you have a boundary condition that's missing and you have, you know, a body that's moving, or, you know, way oversimplifying this, but maybe it's something like, you know, we have not this would ever happen, but
If you mapped to something that, like an element that had zero length or an area to it, you probably couldn't map to it. So
yeah, you could map to it, or if it's not connected or something, right? If for some reason, if, you know, because if you take some potato and you have a program that's looking at this geometry and it's trying to figure out how it's going to discretize this, how it's making this this mesh, it's not always going to be perfect, right? It's not the same mathematics. We haven't talked about that. We haven't talked about how you take a geometry and you apply a mesh to it. That's a whole nother routine and sub application that's going on in a finite element code. We're talking about when you already have this, how do you make sure that the results that we're going to get out of our finite element code are reasonable? And that's what it's checking for. Are there discontinuities in here? Like you said, Jacob, you know, maybe you have, you know, some way that you have an element or something that has like a negative volume or no volume or whatever there may be to it. So you're trying to map from one space to another space that doesn't exist, or whatever it may be. So that's kind of what it is. But what's crazy about it is this is some crazy math, right? It's very complicated and it's very tedious to follow and to make your way through it. But really all we're doing is it's just change of coordinate systems is really all this is. It's change of coordinate systems going from this element here with a 1, 2 to this other C space where we're saying, okay, when we're over here, we're going to call node 1 -1, and we're node 2, we're going to call it 1. And, you know, we have these Lagrangian shape functions that say, okay, you know, N1, shape function 1, we're going to say it has this, you know, if we were to look at this at a graphical value, it has this value 1 here, and it has to be 0 over here. And then we have this other shape function N2 that represents this side over here to help us with that. And these shape functions get a lot more complicated. And I think I have a problem that we can walk through that's specifically just on shape functions that will help clarify those maybe the week after next. Yeah, I do have one right here. So, okay. So we still haven't gotten to the point yet where you can actually solve this with a computer, because we're still dealing with integrals and you can't integrate. You have to discretize that. And that's where we're leading up to, is the most common way of solving these problems. And I'll tell you what the name is. It's called a Gauss quadrature. I don't know if any of you have ever heard that. And the Gauss, GAUSS quadrature it's I don't want to say it has nothing to do with finite element, because that's the way it's commonly used, but Gauss quadrature is just a way of taking closed form type boundary value problems and solving them numerically. It is the most common method for taking this problem that I showed you above and solving it with a computer. So that's the examples that we're going to be walking through is the application of the Gauss quadrature for solving this. But it really isn't a finite element method specifically. And then the other big one that's used is called the Galerkian. Has anyone heard that term before? And that is specific to finite elements. So it's a type of Gauss quadrature that that is used for doing this. So
What was it called?
The Galerkian. So see if I have the spelling right here.
I thought you said Wronskian.
Galerkian. Galerkin. Now, the Wronskian is a way of solving a DE, right? So we're doing pretty good. We're plugging through the finite element. I mean, this is the core of the finite element method. What we've been kind of going over is, you know, we have a weak form. We have to get a strong form. I mean, we have a strong form. We have to get a weak form. We've done that. And then, okay, you know, it's a differential equation. So the way that they're solving this is they're basically saying that we have a bilinear functional, a linear functional, and we're going to create this thing called a trial function and a test function. And oh, by the way, this test function has a string W in it. It's totally arbitrary. And we're going to set that thing equal to 0 to help us solve it, to make most of the equation go to 0. Like at one of the boundary conditions, either at the end or at the fixed point. That helps us simplify that. And we're solving it. This is really just a differential equation that we're solving using these different methods like the Rayleigh-Ritz methods and the theorem of minimum potential energy for taking the derivative of minimizing functions, and ultimately getting this stiffness matrix for the global system, which we saw a few weeks ago, and now we're talking about it at the elemental level. So that's kind of the general process. There's still quite a bit more to go before you could sit down and start plugging this into code, but we're close. Okay. So I think that's it for tonight. I'm out of breath and it's almost time anyhow. So. All right, folks.
All right, thanks.
Yep. Have a good night and a good weekend.